All right, guys, welcome back. Today, we're going to begin our discussion of metabolism in a more detailed way. In the last lecture, we sort of talked about these aspects of energy extraction, sort of a big picture way. Today, we're going to get down to brass tacks, all right, and see how some of the properties of the molecules that are involved in this catabolic breakdown um, do what they need to do. Some of the enzymes that are involved, the energetics that are involved, the reactions and the chemistry necessary for this extraction of these high potential electrons to happen, right? Okay, and we're going to start this process with one of the main, or maybe some ways to think about the main pathway, the central trunk of so-called intermediary metabolism, with the catabolism, um, or breakdown of carbohydrates. And specifically, we're going to be looking at the catabolic breakdown of course, of glucose. All right, which you may or may not remember is a molecule that looks something like this. And we'll get back to some of the details of this in a little bit. All right. Okay. So the goal here is to understand how this molecule gets broken down into simpler molecules for the purposes of extracting energy, right? And we're going to start with this sort of breakdown, this catabolism of carbohydrates, specifically glucose, for a couple reasons. One, for accounting reasons, just general sense of, before one got around to understanding how you build things, how you make biomolecules, you kind of need to know what you got to work with in terms of energy and constituents, right? So that's a good reason to start here. The second reason is historical. This pathway that we're going to be considering was in addition, or is in addition to being generally essential to all cellular-based life forms on this planet, was also the first one that was worked out in any real detail. And the deduction of this pathway sort of grew out of Pasteur's work in the 19th century on fermentation, and into the early parts of the 20th century, where this sort of biochemistry really has its founding in a formal way, right? Okay, so now before we can begin this process, the first thing I need to do is remind you of some of the basic properties of carbohydrates. This is sort of our second class of biomolecules. We've spent a lot of time thinking about proteins, and now we're sort of coming up to spending some time thinking about this second class of really important biomolecules. Not going to have nearly as much time to dwell on carbohydrate properties as we do on proteins. Carbohydrate chemists would consider this a great injustice, but our focus is a little bit differently. But we still need to understand some of the basic properties of carbohydrates, or the class of carbohydrates that we're thinking about here, before we can understand how this catabolic process is going to work, right? Okay, so carbohydrates are the kinds of carbohydrates that we're going to be thinking about, like glucose, are also known, of course, as sugars, right, in common parlance, or somewhat more accurately, monosaccharides, right? Which hopefully you guys all remember, right? And the sugars of the monosaccharides are essentially, if you look at this molecule, you'll get some sense of this. These are essentially carbonyl-containing derivatives of polyalcohols, and they're put together from a really pretty simple chemical formula overall. It looks something like this: CH2ONCO, right? And you just sort of repeat this, right? And you basically build up what is a monosaccharide, right? Now you can make these in a variety of different ways, and a variety of different sizes, and we're going to see some of that. But from each sugar, the class of carbohydrates we're thinking about, the sugars, the saccharides, have a theme in terms of their chemical composition that's very analogous to proteins, right? If monosaccharides are the fundamental unit, like amino acids are with proteins, you can link monosaccharides together to a particular kind of bond known as a glycosidic bond, which we're not going to have time to spend any time really looking at, but is analogous to an amide bond in a protein to create so-called oligosaccharides, which would be equivalent to, say, an oligopeptide in a protein, right? And then you keep going, you keep making these things bigger, and you, of course, can then make polysaccharides in the same way you can make a polypeptide or a protein. Now, the polysaccharides can get quite a bit more varied, unlike with proteins, which are by and large linear chains. Little variations there. When you have disulfide, you can get multiple chains covalently connected, but for the most part, most proteins are a single linear polymer. Polysaccharides can be massively branched, and so they can be quite a bit more complex in terms of their overall constituent types, as we'll see a little bit of, and their general structures. But at the core level, there's an analogy here that's worth remembering, right? Okay. Now, like I said, we got this sort of like, polymer repeating basic unit of the monosaccharides with that N. And as that N expands, you can make bigger and bigger and bigger monosaccharides, right? And these come in sizes from as small as 3, which we're going to see, all the way up to 8, or can in principle and be even more. Though for most of biology, sugar is any bigger than sort of where N was 6. So the total number of carbons was greater than 7, or somewhat more rare. And with the bulk of what biology is going to be involved with 3, 4, 5, and 6 carbon sugars, and a little on the 7 carbon sugars as well. All right. Should also mention another little bit of nomenclature, and we'll just start here with the simplest sugars that we're going to worry about are the so-called 3 carbon sugars, or the trioses. And it's that oses that is indicative of the fact that we're working with a sugar. So triose means 3 carbon sugar, right? And I've shown you one of these before when we were talking about some aspects of basic protein structure. And that was this guy, this simple 3 carbon sugar. Again, there's our 3 carbons. There's our carbonyl. This is, of course, glyceraldehyde. All right. Now, because the carbonyl carbon in glyceraldehyde is an aldehyde, this triose, or this sugar, or this monosaccharide, is also sometimes known as an aldose sugar, right? Because the carbonyl is in the form of an aldehyde. Now, what you may or may not remember is that these carbonyl groups that are alpha, or alcohol groups that are alpha to a carbonyl group, can go through an isomerization reaction in which the carbonyl group migrates. It moves over by 1 carbon, right? And it does this through a particular intermediate that looks something like this, where if we had, say, an acid group here, right, that could donate a proton, we move that guy over, and we had some way to take up that proton, we can generate an intermediate of this triose sugar that would have an alcohol group now at both of those positions, right? And a carbon-carbon double bond. This intermediate is known as an enediol, right? And it's not, make a little more space. Oh, shoot. this enediol intermediate is not simple to form. It does happen. It will happen spontaneously. But this conversion from that aldehyde to the enediol is relatively slow on its own, unless one has a way to do some acid-base catalysis. And we'll see some examples of that when we actually get into the business end of using these molecules, right? Okay, but we don't have to stop there, right? We can continue this process, and this carbonyl group can migrate on over to generate the ketone version of this molecule, which for this simple triose is known as dihydroxyacetone. Or DHA, right? Now, because the DHA, the carbonyl carbon, is now a ketone, this type of sugar is, of course, known as a ketose, right? So we have the distinction in the simple sugars between aldoses and ketoses. The carbonyl is either in an aldehyde or it's in the ketone, right? These guys are isomers of each other, quite obviously, right? If you remember your basic organic chemistry, and they're a particular type of isomer, right? This shift through this enediol intermediate is known, gets a name, and it's known as a tautomeric shift. Right? Which makes glyceraldehyde and dihydroxyacetone tautomers of each other. They're tautomers. Oh, geez. Right? Okay. All right, so that's this idea, this tautomeric shift, the aldehyde versus the ketone positioning of the carbonyl carbon. It's all super important stuff, right? Really important basic property of saccharides, monosaccharides that you need to know. It's going to be universal. You'll see as we make these things a little bit longer. There's one other property you need to know about them. If you look at that carbon right there, there's something else about that particular carbon, the one right alpha in this sugar to the carbonyl, that aldehyde. There's something else you should note about it if you remember your basic organic chemistry. You'll notice, hopefully, or remember, that you can see that this, there's going to be a proton there. If you count substituents around that carbon, there's that proton, there's an alcohol group, there's this methanol-like group, methyl alcohol group, and then there's this aldehyde group. We have 4 different substituents. They're not the same. That carbon's chiral, right? Chirality of the carbon atoms in monosaccharides is a really big deal. It helps set fundamental aspects of their properties. And in general, the rule that's typically followed in determining a particular isomer, so if this one was drawn out with the right projection, this I would probably draw this out as D-glyceraldehyde. And the reason I would throw it as D-glyceraldehyde is in almost most cases that we're going to be worrying about, the D isomer of the sugar is the one that's going to matter. Remember, we have D versus L isomers, and these are stereoisomers, and they get a name, of course. These are, of course, diastereomers. I can write. Right? And in this particular nomenclature, referring to stereoisomers, we're using the dextrorotary and levorotary notation D versus L, right? Which I introduced to you guys when we talked about chirality in the amino acids, right? Okay, and in the sugars, the D versus L nomenclature is usually applied, or the which you're taking with D-glyceraldehyde versus L-glyceraldehyde, it's keyed to the stereochemistry of that carbon that is alpha, that is right next to the carbonyl carbon, right? But you'll notice, as a result of this tautomeric shift to form DHA, the ketose variant of this triose now is no longer, doesn't have a chiral center anymore, right? There's no longer any chiral center in DHA, right? Okay, all right, so that's some really basic fundamental stuff, right, to think about. So next up the line, right, we would have, if we expand that basic fundamental unit of saccharides, we go up another carbon, right? We could go up to now 4 carbon. That would, of course, be the tetroses. There are some important tetroses in biochemistry. There's one in particular, and one important fundamental pathway. Unfortunately, we're not going to have time to go through the chemistry involved in that important pathway. So we're going to skip it. All right. So we're just going to leave aside the fact that there are tetrasugars that are important in fundamental biochemistry, but we're going to skip over it, and we're going to go on to the 5 carbon monosaccharides, the so-called pentoses. Right. All right. So some of the pentoses you probably are familiar with, and there are 4 or so pentose sugars that play really prominent roles in basic biology, basic biochemistry. And here's one I bet you know, right? So we're going to hear 1, 2, 3, 4, 5, right? Oops, let me draw that a little bit better. That's a little sloppy. There. Well, still a little sloppy. Let me see if I can do this. Okay, see if that's better. Okay. All right. So that's very clearly a aldose, right? And specifically, at the stereochemistry again, at that carbon was right, right? This would be D-ribose. Super important 5 carbon monosaccharide, which I'm sure you've heard of, and minimally from the point of view of understanding nucleic acids, right? Right. Okay, and ribose is, of course, an aldose, right? Because again, we have an aldehyde group, right? Okay, now we run the same tautomeric shift with D-ribose. We can then generate the appropriate ketose version of this 5 carbon sugar, right? By moving that carbonyl over 1 carbon. To form, again, depending on, assuming we have the right stereoisomer here, D-ribulose, right? Which is, of course, a ketose. Okay. Now, as I said, for the most part, we're only going to be dealing with the D stereoisomers of the sugars that we're going to be thinking about. There are situations where L stereoisomers come up, but it's relatively rare. And for most fundamental intermediary metabolism, it's the D stereoisomers that are going to matter. The other thing to keep in mind, if you just look at this, you can see how the number of possible diastereomers is going to expand for these molecules, right? As you add chiral centers to these molecules, in general, the number of diastereomers is going to go up as 2 to the n, right? So even for something as simple as like a 5 carbon, this pentose sugar, right, where you got 3 potential chiral centers in the aldose, like ribose, you could have 8 possible diastereomers, right? So this can start to get, in principle, relatively complex. But the interesting thing is, biochemistry seems to only get focused on subsets of these guys, right? So even though the space can be vast, the enzymes that work on these molecules tend to stay focused on a very limited subset, which is why there's only 4 or so of the pentose sugars that are relevant for biochemistry. Okay, next up the scale. We of course go up 1 more carbon to the hexoses. And this is where we have a whole bunch, right? Let me write this out the way I've been doing it before. Right, so we have 6 carbon, the hexoses, of which there are somewhere around 8 or so versions that are important in biochemistry, right? Or frequently utilized, right? Okay. All right, so good example of this is one you just saw, right? Glucose is of course a hexose. Specifically, it's an aldohexose, right? So we can draw glucose out like this. Right? And this would be, especially again, if I had the stereochemistry, assuming the stereochemistry is right, that would be D-glucose. Like I said, which is of course, again, an aldose. It's an aldose. D-glucose is an aldose sugar. Okay, and like same theme, right? We can run this guy through that tautomeric shift, right? To generate the ketose variant of this 6 carbon sugar, again, depending upon that stereochemistry, that neighboring carbon, right? Assuming that guy is right, to form D-fructose, right? Which is a ketose. Okay, so this is the basic idea. Now you can sort of see what I mean when I say carbonyl containing polyalcohols, because that's basically what monosaccharides are, right? And these get elaborated. They get, amino groups added to them and all other substituents and stuff. So the variety of substituents and whatnot expands dramatically. But you'll already notice something. I've written this out. That's glucose, but that's not what it looked like when I drew it out up here, right? Right, this is also glucose, right? You'll notice I've written the structure completely differently. And that's because once these chains get to 5 carbon and 6 carbon and 7 carbon, there is an internal cyclization that is highly energetically favored in terms of the resting or the most thermodynamically stable form of these molecules, right? So the 5 carbon and 6 carbon and 7 carbon monosaccharides don't want to spend most of their time in a linear form, right? They will linearize, and sometimes, and for certain types of chemistry, enzymes are going to go out of their way to shove them into a linearized form. But, given their own choice, they're going to cyclize, right? And this cyclization proceeds as a result of nucleophilic attack of one of these alcohol groups, right? Right, on the carbonyl carbon of the carbon atom that has that double bond O group, right? That carbonyl containing carbon also gets a name, right? It's worth knowing this, right? Because you probably hear me use this term. The carbonyl carbon of these aldose and hexose sugars is sometimes called or formally known as the anomeric carbon. And that basically just means the carbon that has that that carbonyl group, right? Okay, so just to show you this in a slightly different way, I'm going to draw glucose out a little bit vertically, right? So we can keep track of where things are a little bit more easily. Oh, geez. Look at me. I'm so sloppy today. Yeah, okay. I'm making myself think I haven't drawn this out right. Okay, so here is our D-glucose, assuming again that we got the stereochemistry right on that carbon alpha to the carbonyl group. All right, so here we have 1, 2, 3, 4, 5, right? Oops, I screwed up. See, that's why I was trying to be careful, and look what I do. I screw up. Now I got the wrong color. 6. Okay. Now we've got glucose. All right. So what turns out to be the most thermodynamically stable state of this molecule would be for this 6 carbon, and this again, as I mentioned, happens with the 5 carbon monosaccharides as well. But if the alcohol group that's on carbon 5 attacks that carbonyl carbon, nucleophilically attacks that carbonyl carbon, what ends up happening is you form this closed 6-membered ring, which is the way you're generally going to see glucose drawn out, the way I'm normally going to draw it here, right? Where we have CH2OH. There's carbon, that's carbon 6, as I drew it down here, right? That should be obvious because that's the one hanging off right here. There's 6, 5, 4, 3, 2, 1, right? And then their associated alcohol groups. Right? And this structure has a couple of names. Formally, the chemical species that this internal nucleophilic attack that an alcohol group has in that carbonyl group is known as an internal hemiacetal. Right? This closed 6-membered ring is also gets a name. It's known as a Pyranose ring. Right? Because that 6-membered closed ring. Okay. Now remember, like I said, this is D-glucose. Glucose exists in equilibrium, in principle, with its tautomer, remember, D-fructose, which is a ketose, right? So we move that carbonyl group over 1 carbon. We have a molecule that would look like this. Oh, come on. Come on. And labeling as we did before, there's 1, 2, 3, 4, 5, 6. Those are 6 carbons. But now, again, we've moved that carbonyl over 1. So we now have D-fructose. or that ketose sugar, right? But remember, that carbonyl group is still available. 5-membered ring's a pretty stable arrangement if you remember some of your basic organic chemistry. So this alcohol group can attack that carbonyl to now form another closed ring structure of the ketose that, instead of being a 6-membered ring, is a 5-membered ring, right? And it looks something like this. Right? And using the same numbering as I did before, we'd have 6, 5, 4, 3, 2, 1, right? Okay. This, again, it's an internal hemiacetal. This would be, the closed ring form of fructose, and it gets, in the same way that this 6-membered ring structure gets a name, it's called a pyranose ring. This closed 5-membered ring is known as a furanose ring, right? Okay. All right. So with that basic introduction now to some of the fundamental properties and aspects of carbohydrates, we can now start talking about how these molecules are mobilized in order to extract useful potential energy to create our fundamental energy currency in a living cell, ATP.